to Dr. Jeff Abers. Take it away, Jeff.
Well, thank you, Don, and thanks everyone for letting me sort of fill your evening up here. Let me see if I can get there right. This one looks correct. Okay, are you seeing the version of
Looking
this?
good.
All right. So thank you all. Let me just have to move things so I can see what I'm doing better. Um, Yeah, so my name is Jeff Abers. I'm a professor at the Department of Earth Atmospheric Science at Cornell University. And my thing is earthquakes. I've been studying earthquakes um, and what earthquakes do for most of my professional career, which is, as you'll see, long. Um, and so thought I would do tonight is sort of take you on a bit of an arc of a story of how we learn and what we've learned about some of the biggest earthquakes and the faults that make the biggest earthquakes on the planet. It's fishing, so what you're seeing here is a picture of a team on a ship that I was on about 5, 6 years ago, where we were actually fishing out of the water. Ocean bottom seismometer. This is an instrument that had been sitting on the seafloor for 15 months. The orange things on the top are mostly flotation, electronics, and signals. That little ball, that green ball on the bottom, is the sensor that sat on the seafloor and recorded everything that moved the seafloor for the 15 months. And so we're about to get this on board and see what it's doing. We're off the coast of Alaska. Alaska probably this has a story of earthquakes that start, I would, a lot of places, but probably 1964. Good Friday is the day that most people sort of start the earthquake record there. Um, in on that day, some south of Anchorage, the second largest earthquake that we've ever recorded occurred, magnitude 9.2, maybe 9.3, depending on who you asked. And what I'm showing here is some of the pictures of devastation. Downtown Anchorage saw huge amounts of collapse of the ground as it liquefied. The There's tsunamis all across the Pacific Basin, but very large ones in places like Seward on the Kenai Peninsula. This is showing a before and after map of what Seward looked like before the tsunami and where the inundation was. And this really, we sort of knew this was an earthquake current place, but it woke up the scientific community to the really enormous hazards of these earthquakes and the tsunamis in Alaska. It also happened at sort of the dawn of plate tectonics, and people were first really putting together the story of what these big earthquakes were. One of the really noteworthy things that was seen at this earthquake is that in the fjords and peninsulas south of Anchorage, near Seward and Prince William Sound, there were places where there was enormous uplift. So you could see, ground that had been lifted up in some places. You could see barnacles that were 20, 30, 40 feet above what had been high tide before. These are organisms that live in the water. Other places you saw what had been healthy, mature forests suddenly had their root systems drowned and died. And so these are those examples near Seward and several other places. So we saw the ground move up and down, meters all throughout the region. Um, and when people made maps of this, and started to put together, this really became the first big evidence that helped us figure out what these things were, these faults that made these giant earthquakes. So on your right is a map showing the regions of uplift, the regions of subsidence, and there are a few places that had huge uplift and subsidence, but there's a lot on the sort of 2, 3, 4 meters range. And I think you can see where Anchorage is. Actually, that dot's in the wrong place. But but you can see the sort of this thing sticking down here is the Kenai Peninsula. This epicenter occurred in Prince William Sound, where some of these other pictures were taken. Um, what people figured out pretty quickly, and this came from a paper by George Plafker at the U.S. Geological Survey back then, was that in order to make a fault move this much and move over such a wide area, this is several hundred kilometers from the northeastern corner to the southwestern corner in the Kodiak Island, that's this island down in the southwest, required a fault surface that was um, very sort of shallow dipping surface, not quite horizontal, plunging downward to the northwest, but probably reaching the seafloor at the Aleutian Trench. That's the purple line on the left or the black barbed line on the right. And it's where this fault reached the trench that the seafloor was uplifted very strongly, and that's what produced a lot of the transoceanic tsunamis. So this was sort of the first clue that there are these big, enormous faults in these places that we now refer to as subduction zones. We would call these faults megathrusts or subduction megathrusts because it's a really big kind of what we call a thrust faulting earthquake. This happened really at the dawn of the plate tectonics revolution in the mid 1960s. People were putting together the story of sort of how the Earth was put together. And so this is a figure from a classic paper by Brian Isaacs, Jack Oliver, and Lynn Sykes. Brian and Jack were both professors in this department at Cornell for many decades. The map is showing sort of the first global depictions of not just the seafloor spreading system, the double parallel lines, but the subduction zones where there are these deep sea trenches, giant earthquakes, volcanic arcs behind them. So the little cartoon on the left shows sort of a side or cross-section view of what most of these subduction zones look like. There's this red area where the earthquakes occur, where these oceanic plates are diving down underneath the continents. There's also where a lot of the tsunamis are generated. So the circles, the little dots in the middle, are the sources of major transoceanic tsunamis that have been documented. And you can see there's some exceptions, but by and large, these are all happening in subduction zones, what we would now call the megathrust. Um, and this is also where most of the earthquakes occur. This is a map in the same paper showing a global earthquake distribution that we could first put together in the 1960s when global seismic monitoring really became a thing. And you can see that, there's the Aleutian Arc, the Kuril, Kamchatka, Japan, all around the Pacific, these places where oceanic plates are diving under continents. This is a pretty consistent process. Um, but and we so one of the questions that first came up is like, why are these earthquakes so big? Why is this the only place we really see magnitude 8.5, magnitude 9, 9 and larger earthquakes? Um, a lot of this has to do with sort of if you think of what's happening at subduction zones, we're taking these oceanic plates that have been sitting below the seafloor for tens of millions of years, and they dive down underneath continents. So these are pretty quickly compared to how fast heat can move. So this is actually a numerical model that is fairly recent, but older ones sort of look similar. That sort of shows the basic idea that there is this boundary, the top of the downgoing oceanic plate is this white and gray line. And I'm sorry, sometimes these are going to plunge to the left, sometimes to the right. We can never make up our minds in this business. What's the correct way to do this? But the idea is that because this oceanic plate's moving downward, these contour lines are showing lines of constant temperature. It's dragging cold stuff that had been at the seafloor downward faster than it can heat back up again. And it's also making the stuff above it cold, so refrigerating it. That's creating the cold conditions that you need for faults to be brittle instead of having that surface be a hot, mushy place that rocks can sort of flow past each other. It breaks. And we think it's somewhere around temperatures of 300, 400 degrees C, or sort of the maximum temperatures at which faults can behave brittly. So this fault is diving down to depths 30, 50 kilometers. It's doing it at a very shallow angle, so that has a width of sometimes only 50, but it can reach 250, 300 kilometers. The Alaska one is one of the biggest ones. If we were instead to make like a vertical fault off to the right that is in the sort of normal continental material, you see we reach the same temperature much more shallowly, and if it's vertical, that fault's a lot smaller. Because it's a lot smaller, it's going to make much smaller earthquakes. The size of earthquakes turns out to just be related to how big the faults are. And so this really is the fundamental reason why this is where the giant faults are. These places are cold. Also, Alaska turns out to be one of the best places in the world to study these. This is a map showing the biggest earthquakes in the world as well, probably as of today. There really haven't been any more since this map was made on this top 18 list. And you can see of the 18 largest earthquakes recorded, first of all, 17 of them are in oceanic subduction zones. Number 10 is in sort of a subduction equivalent on land. Um, And also, four of these are in Alaska, the Aleutians. Number two, Prince William Sound. That's that earthquake in 1964. The biggest, if you're wondering, is a 9.5 in southern Chile. It's also, because these systems are connected, the Aleutians constitute about 10% of the global volcanic arc system. And I'm not going to really talk much about that here today, but this is sort of the other thing that we sort of think about is, how these places that are cold and make big earthquakes also make volcanoes. The other thing that people started to realize, and it was sort of coming clear, but after 1964 it became super clear, is that these faults are long and continuous. And with time, these great earthquakes occur in different segments and eventually fill up the entire fault segment. So this is again Alaska Aleutian Arc. This is thousands of kilometers long. You can see that big pink area labeled 1964. That's what slipped all at once or within some short period of time in the 1964 earthquake. But then you can see as a patches is 1938. That was a 8.3 in 1938. There's some other ones. There's a big 1957 earthquake in the mid eights. In 1965, Rat Islands earthquake ruptured all the way out to the date line in the Russian border. But you can see with time, um, and except for a couple of gaps, the whole thing is ruptured once. And this sort of makes sense. This makes a lot of sense from the viewpoint of plate tectonics. As the Pacific plate is diving down underneath Alaska, those little numbers on next to arrows are 75, 67, 57. That's how fast the plate is moving relative to North America in millimeters per year. So it's building up, 57 millimeters a year. That's 57 kilometers every million years in geologic time. But that builds up stress on these faults where the two plates are sort of locked together and they eventually have to slip to make a big earthquake. That's how the shallow part of the plate boundaries accommodates this motion. Um, but there's also some gaps, and you can see, right, there's this tiny thing that happened in 1948, but there's a big gap off of the Alaska Peninsula. And so this became an obvious research target. Um, and this actually was sort of the start of my research career in subduction zones. It wasn't what I did my thesis on, but my postdoc at Lamont Doherty Earth Observatory, Columbia University, took me to it was my first trips to Alaska to this gap, the Shumagon Seismic Network. This yellow box here, these is the Shumagon Islands. We'll zoom in on this and I'll show you a lot more about this in the next couple of slides. But this is really what got me started thinking about this problem of how you make really big earthquakes. Um, After this, and I'll sort of walk you through a series of other projects I've done. One called Moose, multi-scale observations of subduction. We have cute acronyms named after animals all the time. We're going to go back to the Kenai Peninsula where that 1964 earthquake started. We'll show you what the ship is about from the more recent Amphibious community seismic experiment. And if we have some time, we'll talk about an earthquake that happened since the pandemic. So this is a blow-up map of that area, the Shumagon Islands. You can see the Alaska Peninsula and these islands that are going way out towards the trench in the bottom. Um, this is much less dramatic since I'm not doing this in person, but this is me in 1990. Okay, I dug this picture out just for this talk. I mean, this is a suit that you have to wear because we're flying around in helicopters and we're flying over this really, really cold northern Pacific water. If the helicopter loses power and you splash in the water, the suit's supposed to keep you warm for at least a few more minutes. And then the picture in the background is me getting ready to sling a load of stuff onto the bottom of the helicopter. Um, as we're doing this. So 1990, 1991, 1993, made trips there as the funding at this point was like winding down for that project. So we were largely finishing it up, removing equipment. But that also gave me a lot of time to look at some data. And so this is just showing I'm going to show one sort of result from analyzing the data. This is again one of these cross sections from somewhere near the Aleutian Trench through, because of these islands, we could have seismometers like way close to the trench, and then the Alaska Peninsula is where the really big volcanoes are, the volcanic arc. So what you can see, these are locations of earthquakes that we were able to get really accurately because we put out these instruments. That this belt of earthquakes that's these are small, most of these are 3, 4 magnitude earthquakes. descends from the trench, which is just off to the right on this picture, um, gradually increasing in dip, how steeply it's plunging down into the earth, but in a very narrow zone. And this is, I think, one of the big realizations. This probably defines the top of the oceanic Pacific plate as it's going down. So the conditions that make these little earthquakes are really only present right at the very top, not throughout the whole plate. The other thing we're seeing is the purple and the big yet red ones are the bigger earthquakes where we can tell what the fault plane was that made the earthquake. And these little things, black lines with arrows, are showing for magnitude 6 to 7 size earthquakes that were recorded when we were there and or while this network was alive. And you can see that basically the planes of the faulting is parallel to the seismicity. This all these earthquakes that are going down from about 25 to about 45 kilometers deep are showing motion on that big fault. So this is the same big fault that could rupture, we call a megathrust, that in other places seems to rupture in a big earthquake. But if you remember, this is where we had a gap. Okay, so that was sort of the first thing that we did, and it did sort of raise the question. It's like, okay, so we're here, there are earthquakes. There's obviously the fault is there, the plate is there. Why hasn't there been a magnitude 8 giant earthquake rupturing through here like there's been in the rest of the Aleutians? Well, the answer came from the other thing we were doing at the same time as we were putting out early benchmarks for early generation GPS instruments that were revisited, but for decades by not our group, but other groups followed up on this. And we were able to see using really high precision geodesy, motion of the surface to within, millimeter to a year accuracy. In other words, we would come back a year later and you could tell within a couple of millimeters how much things had moved relative to before. And what you see, so that's what these arrows are. They're sort of averages from 1992 to 2017 in this particular paper. Um, Off to the east, where the 1964 and 1938 earthquakes occurred, you can see there's really big arrows. There's no scale bar, but these are, on the order of, a large fraction of the plate motion. What's happening is the Pacific plate is moving down. It's locked, it's coupled strongly to this little wedge of North American plate. It's dragging it downward, and that's building up the stresses that'll eventually get released in the next big earthquake. But if you look in that Shumagan Islands region, they're really small arrows. What that means is that that's not happening. What's probably happening is the plate is sliding past each other much more freely. In other words, what we would call a creeping fault. We didn't know this at the time, but the data we collected started to set up sort of this paradigm. So we've seen this kind of transition. So this is what we started with in 1993. Then I had this realization that there, there's a finite but significant system of roads that cross Alaska interior, including going down to the region that ruptured in 1964. And I told my colleague who's at University of Alaska Fairbanks, wouldn't it be fun if we just put a seismometer every 10 kilometers on the entire road system of Alaska? And that's basically what we did over the next 20 years. We got our first project funded in the late 90s and deployed our first seismometers around the Denali area in 1999. We moved south, and then we moved, most recently, we did sort of the um, sort of the eastern part from Delta Junction to Valdez in 2016 to 2018. But there's a picture. The other thing that happened around the same time was the development of really precise but portable seismometers and digital acquisition systems to record them. So this is us loading a truck with 3 seismometers, the sort of big state-of-the-art kinds of things. Each box has one sensor in it in the parking lot in Fairbanks as we're about to head south and put these in the ground. And this is what we did. So the big green spheres and yellow squares are the result of 3 big projects that I helped deploy and was a co-PI on over the years. The Broadband Experiment Across Alaska Range is what BEAR stands for. And then, yeah, more. The other ones have other cute acronym is a bear, moose, and we have wolf. We have a theme going here. But as you can see, this is like most of the road system. There's a few pieces of road that aren't that interesting in the north that we never got to. But we essentially achieved our objective of putting a seismometer every 10 kilometers across the road system. These other dots are other seismometers that are part of permanent or long-term arrays that were put out mostly in the last 10 to 15 years, so toward the end of the time that we were doing this. So I'll talk a little bit about why we did this and why this is interesting. I just first thought I would show you what this was looking like. Okay, so we're using a road system, but we sort of went road plus. So, as we got to the south coast into Prince William Sound, we would charter little boats to take us around. Beautiful spots for looking for things. The last thing we did in Kodiak, we had float plane support, but you can see there's a bear that we saw in the bear experiment. And these last two pictures, I don't know, we always show this. This is what happens if we leave some equipment in the ground for several months and bears come and visit and are somehow unhappy or curious. Um, okay, so this is what I spent many, many summers doing over the last 25 years. Question is, what do we get from it? And the answer is, besides locating earthquakes, the signals that we see from earthquakes can be used to tell us something about what's inside of the earth, something about the composition, the temperature, how much melt is present, or fluids, or whatever. Um, Many of these methods fall under the general heading of something called seismic tomography. We can record earthquakes. Both nearby, what we call local earthquakes. So this is a figure showing lines from earthquakes in a subducting plate going up to seismometers. And they're colored by some aspect of the signal quality. Or we can record teleseismic earthquakes from the other side of the planet. That's like the figure that's on the right. And as the signals travel underneath something that's right below you, differences between the signals you record, you can see. We can measure how long the signals take to get to you, how much energy is absorbed, what the amplitudes are, and we also see like extra waves coming in. And from all of these, we can make some images. So this is just one example showing from just the bear experiment across Denali, an image of what we call seismic attenuation. This is a lot like what a CAT scan does, is it measures how much energy is lost as waves propagate, except instead of using X-rays, we're using seismic waves. Um, and what we can see is, and we quantify, there's a number, this is this Q thing, this is attenuation quantity, but the basic thing about it is energy is absorbed differently depending on things like how hot the rock is, but also if there's a lot of like water being released in it and if there's maybe some melt present. And so we can use this to look down, in this case, underneath Denali, and we can say there's a big region of low Q, so it's a high attenuation north of there, and then the blue stuff is lower attenuation south of there. Q is like the opposite of attenuation. But and so when we think about this is first start telling us something about the temperature structure. We're subducting a plate that's kind of cold, that's bringing in hot material once the plate gets down to depths of about 80, 90 kilometers deep. And there's this cold region in the foreground. And this has a lot to do with how we think, volcanoes and volcanic arcs are produced as a consequence of subduction. We also see areas where we think maybe fluids are being released. So we did a lot of this kind of stuff. We also started to notice, though, that we would see, besides just normal signals, what we call P waves and S waves, a lot of other things. And I'm going to play this a couple of times. This is sort of this is a animation or a model showing, and it happens very fast. Unfortunately, I can drag this around, showing it's a simulation of seismic waves leaving an earthquake that's at this one is about 120 kilometers deep inside of a layer that has a lot of what we call heterogeneity, different kinds of materials layering like we expect in a subduction zone. And you can see that we're not just seeing one or two single arrivals, but there's a lot of other stuff there that's coming in that, as it hits the surface, we can record it on our instruments. And so this is just we use this kind of modeling nowadays. This is from a brand new paper that we just submitted 2 weeks ago to look at how the things we see on the surface are related to the structure at depth. And for example, one of the things we see in a lot of these sort of subduction settings is This is showing what a seismogram actually looks like. Okay, so we record three at each place. The ground moves up and down, and then in two horizontal directions. And it could be north, south, east, west. In this case, there's something a little different, but um, we usually see like on the top, and you see something labeled P, that's the primary or first wave. There's something later, that's the S or the secondary wave. And then we're seeing in some of these places something really big in between. That's like a few seconds after the P wave, but long before the S wave. At first, these things are a little mysterious. They shouldn't be there, but these sort of models that we do inform us that we're probably looking at is a signal. That's another consequence of this subducting plate boundary descending into the Earth. That we're seeing something that spends part of its life as a P wave, hits the surface and converts to an S wave and shows up at this. And there's a lot of reasons why we think this is what this is. So we see these kinds of what we call mode conversions, P waves turning to S waves a lot, but only in sort of these subduction zone settings in a couple of other places in the world. We can do this with local earthquakes. These are showing the same things with teleseismic signals. So picture the signals coming up from below and a little bit off to the right. This is actually stitching together something from Muso. South is to your left now, and north is to your right. And you can kind of see there's like a blip that shows up that we're projecting. It starts off like 40 kilometers deep in the south and gets down to 150 kilometers deep. I'll draw a line so you can see what this is. Again, we think what we're seeing here, and there's a lot more processing or we do with these signals. This is a direct consequence of the signal hitting the plate boundary. There's a really strong material boundary there. And so we can use lots of signals like that to make pictures like this. This is a image. Now what you're looking at is something about how fast waves travel. It's from data like what I just showed you with a lot of processing in it. But again, you're looking at sort of this cross section. The map is in the bottom there through these moose and bear arrays. Now there's 450 kilometers going from the south coast all the way up to near Fairbanks. And we can see this thin red thing. This is a low velocity thing. Material is slower than what's around it. Um, and this pretty much follows the earthquakes down to, well, all the way through, and certainly down to depths of like 40, 50 kilometers. This is where the 1964 earthquake are. We think we're actually seeing the fault zone or the region of the fault zone that's making these big earthquakes. It's a thin, we call low velocity, low seismic wave speed channel that we're able to reproduce there. And so this is like another new thing. Like not only do we see earthquakes following the top of the plate going down, but there's something there. There's something special there. Some of it is we're just subducting oceanic crust, but there's also these wave speeds turn out to be very slow even for that. So we're probably looking at a beat up, damaged zone of material. It starts to look a lot like rocks people see when they go to places where um, some geologic process has exhumed one of these mega thrusts. And this is actually a picture from somewhere in the Italian Alps where a section of Earth's crust is sort of subducted down to here, depths of like 60, 70 kilometers, come back up again, and we see the geologists are able to map this like couple kilometer thick section of highly broken up faulted rocks of complicated compositions. There's a picture actually I took from one of these on a field trip. But the wave speeds and sort of the complexity look a lot like what we're seeing in these seismic images. So we think we're actually seeing now with seismic waves some of the things that geologists have suggested should be there. The other thing we can do is this is just a slice through this section of Alaska, but we've then extended this to like all the other seismometers that have been recorded, all the other arrays. When we finish the road system, other people do other things. This is a map showing how deep that low velocity, that mega thrust is throughout all of southern Alaska. So Anchorage is over here, all the way to the Canadian border, we see this low velocity layer dipping down. This is a through-going continuous big feature. There's a new thing. No one's really seen this before. My former student, Michael, um, published this paper. But you can see that I've drawn here the edge of the 1964 earthquake zone. It didn't go all the way to the Canadian border. This could have been a bigger fault, a bigger earthquake. The fault is there. The earthquake didn't rupture all the way across it. So it's a question of why not. Slight aside, Michael, the student who wrote this paper, is now finishing a postdoc about living in Nome, Alaska, eagerly awaiting for the Iditarod to finish. The finish line is right near his house. This about 2 days away from reaching the end of the race course, I think. So he's very excited about that. Um, that wasn't enough though, because we realized like, except for in the Kenai Peninsula, a lot of this is happening offshore. So, and we need to get back to the Shumagon. So we started this story. So somehow I convinced a bunch of colleagues of mine and the National Science Foundation to give us a big pile of money to go and put instruments not just onshore but offshore in what we call the Alaska Amphibious Community Seismic Experiment. That's ACE. We did this in 2018, 2019. All of these other colored dots with numbers are part of the ACE array. This is just another map that was made by a colleague here at Cornell, Grace Barczyk, where you see, here's the whole system. We're able to put seismometers all the way onto the Pacific plate across the trench now because we can put things on the seafloor. We put them on the shallow water shelf. We put land instruments on the Shumagon Islands, which you might recognize on the sort of western side, and also on Kodiak. Turned out to be a great place to do this. Even on land across the volcanic arc, the little black triangles are the volcanoes. We use OBSs, is what we call these ocean bottom seismometers. We had 75 of those, 30 more on land instruments. On top of, there's a bunch of permanent stations that have been put in all these little white squares shortly before this. We did this for 2 summers and a winter in between. We also put a lot of other instruments, accelerometers, pressure gauges that could help us see small variations in vertical motion, temperature sensors. Some of this turns out to be good ways to monitor turbidity currents offshore. We added extra instrumentation on Kodiak. We set off our own sources, electromagnetics. All of this, we collected this data immediately, went into publicly available open archives. Everyone gets it for free. And so the idea is that to really try to push science to into much bigger sort of community-wide mobility. It's supported by a couple of instruments center. The EarthScope Portable Instrument Center, or EPIC, is in Socorro, New Mexico. It's this vast room full of seismometers ready to go. I was just talking to them just before this call. They're about to ship me 8 seismometers to New Zealand next month for another project. And then smaller scale, but much more complicated technology are the places that build and test ocean bottom seismic equipment. And so this one is one that no longer exists as part of the Lamont Doherty Earth Observatory. They're now all done through Woods Hole. Um, and this is sort of what some of the deployments look like. This is my colleague from Santa Cruz who's installing an instrument somewhere on the Alaska Peninsula. That's that float plane that we use to get around Kodiak. All the purple signal or pink circles that you're seeing are places that we installed on land. I was on the Kodiak team. Susan was on the Alaska Peninsula team. And we left them in. We put them in May, June 2018, came back August 2019. Offshore, this is what a bunch of ocean bottom seismometers look like on the deck, getting ready to deploy. The deep water ones have all this flotation. In shallow water, we worry about trawling and fishing and just wave energy. So they're these like big, solid metal, um, low aspect ratio things that trawlers can drag over the top. They're connecting them. Again, we put these out. This is May and July of 2018. In 2019, we came to get them. The fancy picture on the right, we're using actually an ROV to get the shallow water instruments off the seafloor. You can see a little sensor hanging off the bottom of that big gray cone. And then this is taken, the picture on the left is part of the recovery leg that I was on off of the Alaska Peninsula for the deep water instruments. I remember getting off the ship thinking like, well, it's September 2019. I have no more equipment in Alaska for the first time in decades. What am I going to do with my life? Within 6 months, I was really glad I didn't have equipment stuck in Alaska. But so one of the things that we tried hard to do is to get all of this data out as quickly as possible. Plan on the left is actually from a different project in Cascadia off of Oregon, Washington, looking at just how many people are using data after in a project like one of these. The one on the right is showing something that anyone can pull off of the USGS webpage. This is the earthquake catalog from our experiment. We also used the fact that we had, 5 different cruises going to bring in a significant number of early career scientists, students, graduate students, postdocs to apply to SAIL programs. We brought some K-12 educators from the Anchorage area as part of a teachers on board thing. We had a undergraduate short course in Kodiak, blogs. I think um, total 41 participants who are not part of the PI team or their students. Um, and we collected a bunch of other data. I won't really talk much about this, but it was a great vehicle for add-ons and extra experiments, extra things to happen. Beautiful bathymetry maps came out of this offshore. Um, it was a lot of work. I was the lead of 8 PI, 9 PIs running this, and we 105 seismometers. We had about 3.5 terabytes of data from the long period ones. We had these high frequency nodes on Kodiak. We had another 400 instruments we used every 300 meters on the roads in Kodiak. This is like using up all the roads. The 5 cruises, 112,000 nautical miles is like halfway around the Earth. Total with all the land expeditions, we had 14 expeditions. I bought 73 plane tickets, I think. And then, as someone who does this stuff, you could appreciate that's more than 150 conference calls are on my calendar. Um, and I think over 4,000 emails by the day that we finished data collection. So it's a lot of work, and you have to sort of think about whether it's worth it. Some other things we did with this, we've been busy making catalogs. This is mostly done now. The Alaska Earthquake Center and Fairbanks sort of use their standard methods that they monitor other earthquakes to build this catalog that you're seeing that was released a couple of years ago. Um, we are now here. My colleague Grace Barczyk has been taking the lead to do a parallel machine learning catalog on this. This is a map as of a couple months ago of what they've been able to get using modern methods, several times more earthquakes. And you can see there's like a lot of small earthquakes. The colors are how deep they are. And so you can see they get deeper as you get farther from the trench. That's the subduction zone going on. There's earthquakes seaward of the trench. The map on the right just shows the earthquakes that were only recordable because we had ocean bottom seismometers. So we're learning a lot about not just the incoming plate, but other places where the mega thrust is that we otherwise wouldn't learn a lot. Nope, wrong way. And we've also been, my student Nolan has been working on trying to assess sort of what having all these extra instruments is doing to earthquake location quality. So these little arrows are showing some of the big mislocations that you would have if you only had instruments on land, including the seafloor instruments. So we're really understanding that having instruments on the seafloor near where these earthquakes are super important. We are able to do we're seeing those kinds of P waves turning to S waves I showed you before. So we're making maps of how deep the downgoing plate is on the right, and then other maps showing that it's actually more complicated than that. We're seeing internal layering in the downgoing plate. So our picture of how subduction works has really changed a lot since that early papers from the 1964 earthquake, from having, big fall to general idea to really seeing that what's subducting has a lot to do with how these faults operate. There's a lot of complexity to the system. So we thought, we were all set. This is a paper we just submitted. Those works have been done sort of on that data set. And then this happened. 9 months after we pulled out the last last seismometer, was the first of three really big earthquakes. There's a 7.8 in the date is wrong, so I should say July 2021. The first one was in July 2020. Then there was another one in late fall 2020, 7.6, and this 8.2 was in July 2021. The Chignik earthquake is 8 point. This is the biggest earthquake that the U.S. has seen since 1965, the last one of the big gap-filling earthquakes down the Aleutians. And of course, it's in the middle of a pandemic, and there's a lot of things you'd like to do. Like we wanted to go with ocean bottom seismometers. We couldn't get that to work. But we wanted to record aftershocks of this. So the map on the left shows sort of one estimate of now this is what we can do with earthquakes is what slipped how much. The middle of the earthquake rupture patch may have slipped like 9-10 meters. The little dots are the early aftershocks that were recorded from far away. The other map shows sort of the locations of all three of these earthquakes, and the contours are showing roughly how much slip there was. So you get the feeling like this seismic gap that we saw suddenly looks a lot less like a gap than we thought. And now we're sort of going back and questioning, some of the sort of the dogma of why there hasn't been a big earthquake here. Maybe we had to wait till a global pandemic. But we got a bonus round out of this. My first flight after the pandemic was to go back to Kodiak. Um, I had not been on an airplane, I think, well, it's not quite true, but since I came back in frantically in March 2020. And so I would led a Kodiak group as another team went out to these smaller islands doing you putting again this high accuracy GPS, look at how much things moved, and here we are reoccupying some of the old sites. This is just showing us flying around from Kodiak City to these remote sites. This is data set we haven't actually had a chance to look at very carefully. We have early views tell us that um, the earthquake locations that we're getting without using these stations and just with land stations are biased. They're shifted by 10 or 20 kilometers, and we may have the depths of the fault not quite right. So these are the sort of things we're working on. Um, but yeah, this is turns out to be a region that never quite gives up giving new things, and we've learned a ton. Yeah, I'm gonna stop there, leave you with a couple more pictures of ocean bottom seismometers coming out, and I'm happy to take questions.
Thank you, Jeff. That was great. And
I'll just share.
open up the floor for questions. So you can go ahead and raise hands.
Stop the
We've
share
got
fund.
a large crowd, so I think I need you to use the um, reactions button to raise your hand in Zoom. We've got 122 people tonight, so you've set a record, Jeff. Um, so from those 122 people, can we get a question or two?
Stunned silence.
Yes, indeed, Rob has a question. Go ahead, Rob.
All right. Everyone's just too shocked to
Yes.
know what to say next. This is a very general question, but give a little bit of context. So my career started in Shizuoka, Japan, near the Boso triple junction. So for everybody else, where three plates are coming together. And the entire time I was there, which was a little over 4 years, people were waiting for the mother of all earthquakes. And there are lots of ideas about why there had been lots of earthquakes nearby, but not in this particular spot where they were expecting one. And so what you described, where you had this sort of blank area of lack of activity, reminded me of it, although I don't know if there's any analogy to be made. But I guess my question then is, to what degree are the results of your studies in this area where there's been this kind of, uh, area without as much seismic activity for a long time, generalizable to other such spots in tectonic boundaries around the world?
No, it's a good question. I mean, I think there's so the basic sort of concept of gaps, of gap filling earthquakes and places that they haven't happened seems to be fairly repeatable around at least, it gets not so many earthquakes in some of the oceanic arcs. We don't know much, but certainly through Japan and Kuril, Kamchatka, and then down through Central and South America. Especially, there's been some very well documented patterns that are very similar. And I think in Chile, for instance, you're starting to see a second cycle has started in the last 15 years of these great earthquakes. Though that said, I think the early view of maps like that, people first started making those gap maps around 1970 when they assembled these sort of catalogs. Um, they thought that, well, each of these segments, there's like one size of earthquake that happens, and then another one over here, and they all fill everything up. And that's probably turning out not to be so true. I mean, the fact that we're starting to see these like magnitude 8, 7.8 earthquakes in places that didn't seem to have earthquakes before is a problem. The much bigger, I think, problem with that idea was the 2011 Tohoku, Japan earthquake, right? The 9.0 that caused the tsunami that destroyed the Fukushima reactor. That northern Japan segment was a place that had previously seen in the historic record a lot of sort of magnitude sevens and low eight size earthquakes. And so, if you take this sort of characteristic earthquake gap model, literally the suggestion was that that's the earthquakes that you would have there. And then to have a magnitude nine go through that ruptures through a whole bunch of these at once, make some of the people said, oh, maybe this isn't right. Maybe, different things can happen different times. And then, there's also a realization that this magnitude nine had happened in 840 something or other, the Jogan earthquake. So, there's sort of a lot of crosstalk between people studying Alaska, people studying Japan, people studying South America, Central America, and trying to figure out these systems.
Thank you.
Other questions? Amy, go ahead.
I joined a little late, so I'm not sure if this was covered, but I was wondering if like human activities could induce earthquakes. Like, is that kind of a thing that happens? Like, if people were to mine on a large scale, like, would that be possible?
Um, the short answer is yeah. I mean, there's a lot of evidence that certain places and certain kinds of earthquakes have been attributed to humans. Not things this big by a long shot, but the couple of things that are like fairly well documented. Um, all have to do with putting water into the ground. So if you build a big dam and you flood a reservoir near an active fault, you can change the stresses in the subsurface. And there have been examples of earthquakes that have been produced. I think the Aswan High Dam in Egypt, its maximum height of the reservoir that was designed for, they've never been able to reach because every time they get too high, they start to trigger earthquakes. The other one has been wastewater injection in deepened wells. And so, I was involved in some studies looking at this 10 years ago in Oklahoma, where sort of for reasons having to do with sort of tertiary petroleum production, people had massive volumes of wastewater they started to inject very deep into the subsurface. The biggest earthquakes were made then were, in the mid fives, which is much smaller than what we're talking about. Of course, if they're right underneath a populated area, that the shaking that you're going to see locally can be quite high. So, since then there've been a lot more care looking at sort of what the injection practices and drilling practices are and kind of keeping a handle on that.
So I'll ask a follow-up on that. Those were in the news a lot, maybe 5 or so years ago. Are they not in the news so much anymore because people got tired of talking about it, or did they actually change practices
No.
so they're not happening as much?
Well, the ones in Oklahoma have gone way down.
Yeah.
There was a while around 2014, 2015 where Oklahoma had more earthquakes than California located, and that's no longer even remotely true. There have been there was I forget the year, but more recently there was a magnitude 5 point something in South Korea that seems likely to have been induced by injection, and there've been much smaller events in other places, but people have felt this is mostly from people trying to figure out how to dispose of large volumes of contaminated fluid and just pumping it deep into the ground. And every time you do these sort of the basic monitoring method is putting a lot of seismometers on the ground. If you start to see small earthquakes, you stop pumping so much,
Yeah.
keep monitoring the pressures, and that seems to be what's working so far. But it's an endless
Right.
thing to keep up with.
Other questions? Well,
In the chat, maybe.
um, just a thank you. Oh no, there are two messages in the chat. Let's see what's there.
Oh, obviously one.
Uh,
For me.
Neither are questions exactly, but Marion's got a question. Go ahead, Marion. You're muted, Marion.
Sorry
There.
that I couldn't get my digital hand up there to react, so I did it this way. On one of your early slides, I don't know, somewhere in maybe 4 or something, as I recall, you were showing a wide area coverage from ocean up through the land in Alaska, including about where the trench was and Anchorage and so forth. And it looked to me on the seafloor like magnetic reversals were shown, like you see on
Oh,
either side of. Was that the case?
yeah, I think I had a couple of maps where
And that was
you
quite
know,
complex, I
directly.
thought.
Yeah, I think let me see, this is the probably this slide here.
No, it was the whole
Or
screen, as I recall.
yeah. Sorry, I'm not
There,
in
that one.
yeah. I mean, it's the same thing. This is yeah. People have reconstructed magnetic anomalies, and they're recording, 50, 80 million year history of the Pacific plate separating from other plates, and this sort of the strange shape that's like a little T junction is
Yeah.
what had been a triple junction. There you see a Pacific plate was separating from what's called the Farallon plate to the east. That's the last remnants of it are now the Juan de Fuca plate subducting underneath Washington, Oregon, and something else called the Kula plate. Kula is a word that means like gone or forgotten or something in some Aleut Inuit language. I can't remember what language, but the idea is for the magnetic anomalies, something was there that was spreading away from. There's no pieces left of that plate, so we don't see it. But yeah, this is something that people have, by looking at magnetization, have sort of pieced together over a couple of decades and got, yeah, a real neat sort of idea of the history of seafloor spreading.
Thank you.
Sure.
And there's a comment, not so much of a question, but a comment in the chat about in West Texas, we have been dealing with injection-induced earthquakes the past few years, several 4 or 5 magnitude earthquakes.
Yes, that's also been happening more recently.
And a different flavor of question is, how did you end up in this career? What got you interested in studying earthquakes?
It is like there's different career paths, and when I was giving like graduation speeches last couple of years, you see the lineup of your seniors who are graduating, and for some people, they just know from a young age they're really into rocks or they're really into the geophysics and the planet, and they're like gung ho, and they start as freshmen, but. Um, there's not that many people like that who go into geological sciences programs. And I think, I sort of fell into this midway through college. I like doing physics, and I took my first geology course, and then someone said, "Hey, here's like a major you could do that you can, use a lot of the physical sciences background, but actually get to go outside." And I said, "Oh, this looks great." And so then I applied to graduate school, and my graduate program sent me to Papua New Guinea several times, which was a whole other experience. Um, and then, after that, it got me flying around in helicopters off the Alaska Peninsula. I said, "Yeah, sure.
That's
What's
a
there to complain about?"
that's a good answer. That's a good answer. So, was your undergraduate degree in?
Oh, sorry, worse than that. The guy who has his hand raised is actually my TA in my first ever geology class. I'm just gonna.
Very good. So go ahead, John.
You weren't supposed to mention that, Jeff. My question is, how big an earthquake can we expect on the San Andreas?
This is sort of a trick question coming from John. Uh, the lore that there's sort of a southern section that has a history of earthquakes that, closer to Los Angeles, and there's a northern section that San Francisco and farther north. Each of those seems to have seen magnitude 7.8, 7.9s, and there's a section in between that now and seems to be one of these creeping sections, like the Shumagon Islands section out here in Alaska. But there's certainly seeing what have the creeping sections can sometimes not creep like we do here, and thinking and about scenarios where a really big earthquake gets fast enough running start at one end to propagate to the other end. People have hypothesized a bigger earthquake, 8 point something, low eights, that would rupture all of California. But there's no actual record of that ever having happened.
Okay, but that breaks your rules. I mean, you said that strike slip faults shouldn't be that big usually.
Well, 8.2, 8.3. There's what rule? They're not, it's still a much smaller, well, it's a very long fault, I suppose, if that would be like a 1,000-kilometer fault, but it's only like 10 or 15 kilometers thick. When the Chile earthquake was a 1,000-kilometer long fault, that was 50 or 60 kilometers in the sort of down dip direction. So much bigger.
Good answer. Good.
I learned well from the pros. This is true. John was my TA in my first geology class. So.
Great. Other questions? Go ahead, Kyle. Good to see you, Kyle.
Hey, good to see you too. So in the slide you had where you showed what was underneath Denali,
Mhm.
and it had the different zones of red and blue and stuff like that. Was the red a zone of increased temperature? And if so, could there be magma there?
Yes, we're pretty sure that the red corresponds to a zone of increased temperature. And then, turning those numbers into temperatures, and do we need something more than just temperature? Um, that's been something actually we've been arguing with a lot about since we first did that. And we've done similar things several, in Central America and South America and New Zealand. It turns out that the red under Denali is actually less red than underneath places where we see volcanoes. Like we go to Nicaragua and it's like the energy loss is 2 or 3 times more. So we think, there might be melt that's lurking underneath Denali. There's one tiny volcanic center that had one eruption that is sort of just a little bit east of where we put our seismometers, Buzzard Dome. But it's Denali is in a place where if you sort of follow the contours of the slab farther west, you start to see big volcanoes in Cook Inlet, Mount Spur, Mount Redoubt, and so on. So it's sort of a place where you might expect a volcano, and this is like one of the reasons why we're sort of puzzling about this. But so I think we're not sure. I think it's likely, but
All right, thanks. Good talk.
good question.
Other questions?
I'm just going to shout one out if no one else has one. Jeff, if you could do anything next to carry on your research in that area, and whether it's more seismometers or some other piece of equipment or some long range plan, what would you most like to implement?
That's a good question. I mean, so the things that we've actually tried to figure out how to do, there, there's been a lot of new tech in being able to produce and use not just, dozens of seismometers like I did, but using maybe simpler instruments, but having hundreds or thousands of them that are very easy to put in the ground. So I didn't show you, but I said we had put 400 instruments every 200 meters down the entire road system in Kodiak. That is being a really interesting tool for looking at in much finer scale what that fault zone is looking like. And there's still, that's a data set we're still grappling with, but doing that same kind of thing in places where we right on top of the middle of the biggest slip in the 1964 zone would be fun. Related to that, getting even more signals, people are using fiber optic cables and shooting lasers down. They bounce off of little imperfections in the fiber optics and come back, and you can measure sort of by very tricky things with lasers and interferometry, very tiny little fast motions of changes of the particles. So you're measuring how the cable changes in length. The result is you can turn a cable that might go like tens of kilometers or all the way across Cook Inlet into essentially a seismometer every meter by doing this. So you have thousands and tens of thousands of instruments now all of a sudden. And that's a technology that people are just figuring out how to use right now, but I think is gonna really revolutionize our ability to sort of over long term see what happens. You run these cables out to the trench and just leave them there and not have to go back and get them. And
That sounds amazing.
That's very cool. And I see Karen has unmuted herself, which makes me suspect she's going to ask a question.
I'm curious about some of the other places that you've been and done research, and what sorts of differences there are in the research that you've done in different places.
oh gosh, so lately, most recently, the other place I've been working has been in the Pacific Northwest in Washington and working on a new project in Oregon. Um, and for various reasons, my work there has been more about the volcanoes. We're trying to can we see where the magma chambers are, how big they are? Can we find developing new tools for like looking at magma chambers under volcanoes that haven't been imaged before? How does the shallow plumbing in the upper crust right before it erupts connect to deeper sources of magma, where it comes from? Can we be monitoring deeper? So we're asking a lot of those questions there. The project in New Zealand that I'm negotiating for ship time on now. We have funding if the government actually gives us the money they promised. Um, and just to do a similar but smaller scale thing, but around, again, it's more of a volcano problem. Off of Auckland, the city of Auckland turns out to be built on a bunch of very young cinder cones that have magmas that the geochemists tell us come from very, very deep, 70, 80, 100 kilometers down. And so we're trying to see if we can find the source of those magmas and understand that. Did some other Central America stuff that was a little bit in between, where we were out on the thrust zone and going across the volcanic arc in Costa Rica and Nicaragua. Um, and then there was this other side of my career that I used to do that got me to places like Papua New Guinea, where we were looking at rifts and ocean basin forming processes and uplift of islands and things like that. Again, using a lot of the same kind of seismic imaging tools. So there is a few others. And we, yeah, are doing stuff around here too. Just
Interesting. Thanks.
Go ahead, Marion. Got to unmute yourself first, though.
You would think I would know by now, but I don't. Anyway, out of curiosity, you say you're working in Washington and Oregon. As I recall, that's where the Juan de Fuca plate is subducting. And historically, there's been some pretty big quakes that threw tsunamis way inland in Oregon. Has there been any more study on that to see how likely that is to occur in the next 500 years or so?
yeah, no, there's actually a ton of work being done to instrument both setting up early warning systems near the coast and also putting a lot of this new offshore technology out on the seafloor. Um, what's really interesting is unlike Alaska, where we can put down a bunch of seismometers for a year and get tens of thousands of earthquakes. There's almost no earthquakes at all that are associated with the fault zone at sort of days, weeks, months, and the microseismicity. I would joke when we put that moose array out in the Kenai, we picked up in a year, I don't know, 12,000 earthquakes we were able to locate. At the same time, I had a project going in Washington where we picked up 42 earthquakes.
Wow.
So, but, the big but is that there's a lot of pretty clear evidence that in 1700, there was a very large earthquake that occurred in Cascadia that caused, tsunami and inundation in a lot of the coastal places up and down Oregon and Washington. Tsunami was well documented and dated in Japan. That's how we know when it was, really. There's tree ring evidence of trees that were submerged, like the ones I showed you in Alaska. So, that's kind of the background. And so the work goes both people looking for anything that's moving and deforming now. There's actually a lot of evidence that parts of Cascadia, the plate boundary doesn't always slip in earthquakes, but it'll go in sort of slow events that might take like a week or two in some places, but not in others. And or some of those things may be precursory to earthquakes. We don't really know. So a lot of that work has been going on, and then also looking back at the paleoseismic, the geologic record for evidence of older tsunamis, older inundations, and things like that. Um, and I think this is pretty clear evidence that there's been a bunch of these. The debate right now has always been like one big one and one big magnitude 9. That's sort of the scale is, or is there like, a series of magnitude 7.5s and 8s that have marched up and down the margin in the span of a couple of years? A lot of the geologic proxies don't really have the resolution to tell something that took 2 minutes from something that took 20 years to happen. So, that's kind of where the debate is right now.
Okay, thank you.
Other questions? Maybe one more? And I put in the chat both the link to donate to support us and what's coming up, and I put in the title and speaker for 2 weeks from tonight. If anyone's got another question, we're glad to hear it. All right. Well, perhaps we will say good night and a big thank you to Jeff for a great talk. And
Well, thank you all for coming.
yes, and our record-setting crowd of, I think the biggest number I saw was 122. So
Great.
thanks.
Thank you, Jeff.
Thank you.
Thank you guys. Oh, this is fun.
Thank you all. And I'm going to click the end button and we will see you in